Welcome everyone to our first webinar of the RAS Users Group series. I'm Christy Riley. I'm the Division Chief of the Hydraulics Division here at HEC. We develop HEC-RAS, and we have a lot going on within the division and development within RAS. And we wanted to take the opportunity to make sure we're sharing with you all some of the advancements that we've been making. So we recently released RAS 7.0, and so we wanted to make sure that we were letting everyone know the advancements that we're putting in. It might be a surprise that we had a 7.0 since we had a number of beta versions of 6.6. But we decided with pulling the beta tag off of the pipe networks that it was considered a major feature, and we wanted to have it be a RAS 7.0 release. So that's what we're going to be focused on today is the pipe networks, but we also have 3 more webinars coming up. We have 2 next week to just talk about some of the additional advancements in RAS 7.0, as well as 2D bridge scour analysis and secondary currents. So those will be next week. And then the following week, we will have a webinar for updates on RAS 2025 development, new features. We plan to record all of these videos. We're going to post them on our YouTube channel when we're done. We released RAS 7.0 mid-April, and we also just wanted to let everyone know that we are working on a 7.01 bug release. There was a bug with bridge scour and some other minor fixes that we wanted to get out. One other thing to mention about the release is 7.0 is our last feature release of this line. So if everything goes well, you will only be seeing a 7.01, 7.02, 7.03. We don't really plan to have a 7.1 or a 7.2. All new development is going into RAS 2025. But we will continue to support this version for years to come. So now I'm going to turn it over to Eric. Before I do want to introduce him. Eric Tichansky has been with the RAS team for about 4.5 years, which seems much longer than that. When he came, he took over the technical lead for pipe networks within RAS. He's done an absolute fantastic job. And he's going to take the time today to kind of walk you through what these advancements are in RAS.
Hello, everyone. I'm Eric, and I'm excited to tell you guys about the latest pipe network developments in RAS 7.0. So as Christy said, in RAS 7.0, we took off the beta tag from pipe networks, and we'd had that beta tag on there for some time, and so we're very excited to share that with you guys and kind of catch you up on all of the features and additions that were added during our beta period. And so that's what we're going to do today. So our objectives for today are I'm going to provide you guys an overview of modeling urban systems with HEC-RAS using our new stormwater pipe networks. And this is in version 7.0. With that, we're going to learn how stormwater networks are defined in RAS. We're going to learn about how to visualize output for urban modeling. And then I'll also walk you through some examples, some common things that you'll come across while you're doing urban modeling and stormwater, and some ways to handle those. I'm going to walk you through the methodology. Then we'll talk about geometry data, so how nodes and conduits are attributed and how to build a pipe network. We'll briefly talk about boundary conditions, and I'll show you how to access results. And then finally, we'll close with some fun examples of common applications for using stormwater pipes in RAS. So first things first, kind of the big headline here is that now with stormwater pipe networks in RAS, we really offer an integrated approach to riverine and stormwater flood modeling. And so in the past, maybe some of you have done this. You wanted to use RAS for our robust 1D and 2D surface models. But you also needed to model stormwater pipe networks, and we didn't have that ability. And so one method that people used was to compute their stormwater networks in some other software, usually an EPA SWM-based software, and then pass boundary conditions back and forth. and this is awkward, and it doesn't often work great. And so now you don't have to do that anymore. With HEC-RAS, it's an integrative approach to 1D, 2D surface models and stormwater pipe networks. In addition, you guys are pretty creative. I've seen some really creative workarounds to model pipe networks in RAS and 2D surface models, such as culverts and ditches and burning channels in. So you don't have to do that anymore either. You can actually model those pipe networks directly. So what are they? So pipe networks in RAS allow you to create nodes and conduits, create a network, and then integrate that with your existing surface model, whether that's 1D or 2D. We're really excited about this because it really expands the applicability of RAS for urban and interior drainage modeling. So this type of modeling is becoming more and more popular, and it's becoming more and more required for studies. And so the timing for a pipe network's very excited about that, and that you can build these pipe networks in your existing model, and that allows you to much better assess the pluvial flood risk, and then also analyze the adequacy of existing stormwater systems. Let's start with our methodology. We're going to go through briefly how RAS computes pipe networks. So first, like lots of different pipe network models, we're node and conduit based. And so a user defines nodes and conduits in the geometry. So I got a picture of that above. The purple conduits with the different colored nodes. I'll talk about why those are different colors later. But the user will go in and define attributes for nodes and conduits, such as the invert elevations, base areas, the roughness, that sort of things for your system. And then what we do is, with that information, we'll actually create a computational mesh. And so this is just like what we do in 2D, where we're using subgrid bathymetry. We make cells and faces, and then we compute property tables for them. So this picture on the bottom, I've emphasized it. The mesh is bigger than the actual pipe here, so you can see it. But here's the pipe network mesh that we created from the attributes above. And so what we do with those property tables for the cells and faces is we take them into our 1D finite volume solver. And so the foundation of that solver is actually our 2D solver that you guys are familiar with. So many of the options you get with the 2D solver, you get with our 1D finite solver for pipe networks. And mainly the ability to choose which equation set you want to use. So we offer the full shallow water equations. You can also use the local inertial approximation, where we're just using the local acceleration, or you can take out both the acceleration terms and only use diffusion wave. And so with our methodology of computing property tables, having computational faces within conduits, it gives us the ability to account for a lot of different hydraulics within pipe networks. And so we account for all the basic stuff like pipe friction losses and junction entrance and exit losses. But what's kind of unique about RAS is that we can also use your geometry. Because we're geospatial, we can use your geometry and compute different losses automatically, like a pipe bend loss. So if you had a conduit that makes a sharp bend, we can look at that geometry, find the angle, and then compute the loss that's associated with it. Similarly, we can do that at junctions as well. We have multiple angles coming into a junction. Or if you have plunging happening, we can compute plunges as well. And so because we have those faces within the pipe network, we can detect where plunges are happening, and we can handle those cases special. Finally, we have the ability to compute internal hydraulic structures, weirs and gates in the pipe network. So our methodology allows us to do all this stuff and more. We're really happy about the approach that we took to that. So let's talk about some advantages to this approach, particularly compared to like a 1D finite difference approach. With the 1D finite volume solver, we've got really good stability at low flows and steep slopes. Those are not a problem with pipe networks in RAS. And we have stability through flow transitions. And so pipe networks can handle open channel flow and then transition to pressure flow and back. And they also can transition between supercritical and subcritical flow. Actually, in the picture on the right there, we're seeing just that. The little red line on the profile plot is the critical depth. And you can see that some of this pipe network is below critical depth, so we're computing supercritical flow through there. And then we have a jump and pressurization that's happening within a conduit. And so all of that is an advantage of the approach that we took. So you can compute plunging flows as well. I mentioned that on the last slide. but that's very common in stormwater pipe networks, particularly when we have these big deep tunnel systems where surface pipes are plunging flow into the deep tunnel systems, and we handled that very well. Really, the two unique things about our approach is the faces and the cells, how we can take a conduit and you get to decide how much resolution you want for a particular conduit. So you set the cell size. If you need more resolution in some areas of your model, you can do that. And that really gives the user a lot of tunability to determine where they need resolution and not. And then also, with this approach, we can know what's happening within a conduit. And so for a lot of finite difference models, they're actually just computing node to node. But since we have faces within a conduit, we can actually know that, hey, this conduit is half submerged or half pressurized, or maybe it's half supercritical flow. And those really affect conveyance. And so that's a really big advantage of our approach, is that, yeah, you have this in-conduit resolution to the hydraulics. The disadvantage, though, is that compared to very simple approaches for pipe modeling, these node-to-node computes, our computes are longer than them if we compare just pipe network to pipe network. However, once we start integrating surface models, they get much, much more comparable, as our surface models are quite robust. Okay, so wanted to show you sort of a fun trick that we're doing in order to compute pressure flow and surcharging in conduits. Because we're using subgrid bathymetry, we have these property tables, we have to account for when the conduits get full. So what we're doing is we actually have these negative curves. So we have a positive component and a negative component to each of our hydraulic property curves. So we compute both of them, and the resulting curve is what you get in the solution there. And so we have these positive and negative property tables. We actually have a loop that computes both of them. It's kind of a cool trick that we're doing in order to use our 2D finite volume solver foundation. So that was the overview of how we are computing pipes in RAS. Now I'm going to walk through what we're doing in order to help you build models quickly. A lot of pipe networks, cities, municipalities have their pipe network data in GIS databases. And so they have either shape files or some kind of GIS format that shows where their nodes and conduits are, and they have attributes. And so what we do is we allow you to import directly from GIS. And so what I'm showing you on the right there is our fancy importer. And what you can do is you can remap the attributes from your shape files into the attributes that RAS needs. Various invert elevations, conduit types, that sort of thing, shapes and sizes. You can import those directly and really get to modeling quite quickly if you already have that data available. Another method that you can take is to import directly from EPA SWM. So if you have an EPA SWM based model, if you have an INP file, this is the input file for SWM, you can go point to that input file and we will bring in the geometry from the SWM model. And so we wanted to do that because SWM is the industry standard for stormwater modeling, and we know there are a lot of SWM models out there. And so if you have a geo-referenced SWM model, you can really get a RAS model running quick by importing that in. And so what we do is we look at your geometry, and we also look at the attributes of all the nodes and conduits, and we map those automatically to the RAS attributes that are needed. So really, really handy tool. If you already have a SWM model available, you could get a RAS model up and running quite quickly. But you also have the ability to draw from scratch right in RAS Mapper. So I'll show you what that looks like. First, you'll start with adding nodes, and these are just points in RAS Mapper, so you can place points using the tools that you're familiar with. And where do you place them? You'll need them wherever you have two or more conduits that meet. So that's what we call a junction. Or if you want to make some connection to surface elements. So if you have a culvert opening, or if you need to add top or side inlets to represent curb inlets or manholes or access holes, these are locations that you'll need nodes. In addition, if you have some external boundary condition, like you have an upstream flow hydrograph, a downstream flow hydrograph, or maybe a normal depth, you'll need a node there to attach a boundary condition to. So for conduits, once you have nodes drawn, you can draw a conduit in between them, and you can see the image on the right. We've got some nice snapping features that make it easier to draw conduits. Things to know here are you want to draw your conduits in the positive flow direction. This is good. It's not required, but it's good because it's going to help you better understand your network as you're drawing that. And also, we're using that conduit direction to account for these minor losses, these automatic minor losses. And it's best to keep them in the positive flow direction so that we can compute the minor losses appropriately between conduits. Another thing to know is that the length of the line that you draw is the computational length of the conduit. And so there's not a length attribute that you set like other models. Because we're georeferenced, the line length in GIS is the computational length as well. So that's good to know there too. Some handy tools: you can split a conduit if you need to add nodes in between. Say if you wanted to add a drop inlet between two conduits, you'd split it. We'd add a node there automatically for you. You can also use our quick draw mode. And so what that is we will automatically place nodes as you are drawing your conduits where you are. So as you complete a conduit, we will place nodes, and that really helps you get a pipe network up and running quick. Wanted to briefly talk about node attributes. A few node attributes I wanted to show you. So first, invert elevation. Pretty self-explanatory there. That is the bottom of the node. I've shown you there on the bottom. But something that's unique to RAS is that we use a base area attribute as well. So you might ask, well, what is a base area? Well, that is actually the size of the junction node itself. And so we're looking at the area of the node. And then with that area, we can compute the volume property tables, the elevation volume property tables. And so if you know that your junctions in your system are of a certain size, you can add that into your RAS model, and we will account for that storage within your system. That's pretty unique to our approach, is that not a lot of models will let you do that. And so, yeah, if you have those base areas, make sure you set them in there. So the other important attributes here are top inlets and our side inlets. You can attach a top or side inlet to a node, and then that allows you to connect to some surface element, either a 2D area or 1D elements. And this is where flow is allowed to enter into your pipe network or come out of your pipe network. So let's go look at what the inlets attributes look like. Here's a little diagram of what we're talking about when we're talking about top inlets and side inlets. And so the top inlet is oriented horizontally on top of your node. And you would use this to model things like manholes with or without covers. And so we have an option that allows you to only surcharge flow. So that would be if a manhole cover is on, we don't let flow in, but we will let flow out. You'd use these to model graded street inlets, or if you have riser structures and you have this overflow inlet on the top of your riser structure, that's where you'd use a top inlet as well. So side inlets are oriented vertically. You'd use these for like curb cuts and curb inlets. And then also if you have a riser structure with some side orifices on them, like restrictors or bleeders, this is where you'd use a side inlet. And I've got some examples of that later in the presentation. So attributes are mostly what you would expect. We need some dimensions from you. And for the side inlet, we need the shape as well. What we'll ask is that you provide us a weir and orifice coefficients, and you need both of them. And that's because we will compute either weir flow or orifice flow, whichever is hydraulically appropriate for the given time step. You'll give us both, and then we'll decide whether it's weir or orifice flow at the inlets. And then finally, I mentioned this with the manholes already, but we have an option to only surcharge out of the inlet. And so what that means is flow cannot enter your inlet from the surface, but it can only come out. So that's for modeling an access hole. So where are the top and side inlets? Well, if you look at the tree, they're under pipe networks nodes, and you'll see the top and side inlets down there. And so the reason we did this is because you can define your top inlet or side inlet once, and then you can attach it to however many nodes you want. So instead of defining them in the node, which is what we were doing previously, now you define them in the top and side inlets tables, and then you reuse them everywhere else, which is really nice. Okay, so I wanted to briefly talk about node types. Node types are an attribute of nodes in RAS. RAS computes these node types automatically. These colors in the tree here on the right, we're showing you what type of node each of these nodes are in your pipe network. And so what we do is we look at the node invert, we look at the corresponding terrain elevation, we look at the conduits that are connected and the sizes of the conduits. And based on that, we determine how this node will interact with the surface. And so, for instance, we can determine whether the node is a culvert opening. So if it is exposed and is essentially an open pipe, we'll determine that, and that node will get a culvert opening type. Otherwise, it could be a start or a junction node, or maybe even an external. And so this is where the node type determines how we interact with the surface and determines what kind of boundary conditions are allowed. And so just for the example here, you can see at the very downstream end, I've got this yellow node and it is an external node. So we'll have to put a stage boundary on that. The red ones are our junction nodes, so just connecting two or more conduits. And the green nodes are our start nodes. So these little laterals are saying, hey, this is the upstream end of a pipe run. And so that's where our start nodes are. And then you also have a culvert opening at the very bottom here that's draining the ditch. So another thing that's nice about this is you can open up Mapper and you can very quickly get a visual and determine whether or not you have the right data set up, because you can see what type your nodes are. It's very quick, easy inspection to perform. For conduit attributes, mostly what you would expect. So you need to give us a shape, you need to give us a rise and span. Oh, and by the way, we got lots of shapes to choose from. I think we have something like 8 or 9 different shapes to choose from. All of the same shapes that we have in our culverts, you can use them for pipe networks as well. So you'll need a roughness and need a Manning's N, and then entrance and exit loss coefficients. So these are where flow enters a pipe or exits a pipe. Things that are maybe foreign or kind of unique to our approach is that one thing is we use offsets for our conduits. So what we do is we look at the invert of the node, and then to get the conduit elevation, you set an offset. So I'm showing you this in the picture here that if you have a conduit that is plunging into a node, you'll want to have an offset to raise the elevation above the node. Otherwise, they're most often just set to 0. And so the conduits get the node elevations that they're connected to. So that's a nice thing that you don't have to enter those elevations explicitly. We'll grab them from the nodes. And if you need to modify them, you can with offsets. Mesh cell length, you get to decide how detailed you're computing, how many cells you get in a conduit. And then modeling approach, I'll talk about this more later, but we have 2 different approaches for conduits. You can decide whether or not they're completely hydraulically modeled, or you can actually remove them from the mesh. That'll save computation time, and I'll give you an example of that later. Another attribute are control structures. And so this is where you can, on a conduit, decide, do I have a sluice gate, do I have a flap gate, or do I have a weir? All the data that you're entering in to attribute your system, it all is happening in the tables within RAS Mapper. And so you have nodes, conduits, and your inlets tables. And this is where you're entering data. And so first, the white fields that you see in this example here, these are the ones that you'll have to fill out as a user. So either you import data to fill those out, or you go in and enter values for these locations. So those are the white fields. Based on what you enter, we will calculate the gray fields. And so it might be hard to tell in the picture here, but there are gray fields in here too, and those are RAS populated fields. So a lot of these are informational fields that are to help you attribute your pipe network. So we have a status that'll tell you what kind of node it is and whether it has any problems, or whether it has a top inlet or not, that sort of thing. And so as you're going through and populating data, we will show you where there are problems. So we have red outlines for missing data or an input problem that will prevent a run. And then we also have orange outlines to tell you, hey, here's a warning about what you have set up here. And if you hover them both, you'll get nice little tooltips that'll tell you exactly what the error is. So this one is telling you about your base area. You have a culvert opening, but you can't have a base area on a culvert opening, so we're just going to ignore it for you. And then on the other one, we're just missing data. So if you hover that, you'll see that we're missing data there. We'll also show you these in the error layer. So you can show them all in one place in the error layer, and that helps you as you're going through attributing this data. Looks like a lot, but we have lots of tools that are able to help you along the way, get your data in the right spot. Things that we have added more recently are hydraulic structures. And so you can have hydraulic control structures inside of your conduits. So our first kind of set of structures are gates. And you can choose between a sluice or a flap gate. So I got the picture on the bottom left here, this control structure. So this is a picture from the attribute table. So when you select a conduit, you can tell it that, hey, I want to put a sluice gate on this thing or a flap gate. The flap or sluice gate will be assigned at the downstream end of the conduit. And it can be completely inside the pipe network, or it can be sort of the interface between the pipe network and a surface connection. And for sluice gates, you can operate them just as you would any other gate in a RAS. So we can use rules, we can use time series elevations, or you can use elevation controls. So I wanted to show you this example here. Before I play it, I'll give you a little rundown. So on the upstream end is a large subsurface storage tank. It's in a highly urban area, and stormwater is detained in this tank, and then we slowly let it out through a gated orifice. As I hit go here, you'll see the water surface elevations rise, and then the gate opens and allows flow downstream. And actually, the river comes up on the downstream end, so you'll see the conduits kind of pressurized all the way back up close to the gate. So you can see the gate opening there, allowing water out, and then the conduit is wetted, and then finally the downstream river comes up there, and you get that pressurization. Okay, so you can also add weirs. A little bit different from gates. You actually designate a conduit as a weir. So a weir's not assigned on the downstream end. You just say, hey, this conduit should behave as a weir. And it's also under this control structure attribute. Really what it is that it's a raised computational face. So it's essentially a short conduit, and we're raising this computational face, and we'll compute weir flow over that face. So what's nice about these is whenever appropriate, we'll compute weir flow or pressure orifice flow if needed. So whatever the hydraulic conditions are, we will transition between weir flow and orifice flow as the system pressurizes. And just a simple example on the bottom there, you can see I've got my weir defined right in the middle here, and we have critical flow happening over the weir, and it's backing up water in our upstream end of our conduit. So maybe what you would do is you'd have a diversion at this weir to take flows either to your treatment plant, or maybe it's to an outfall. Just briefly, you don't actually have to define any boundary conditions for your system. If you are connected to the surface, if you have different inlets defined on your nodes and you're connected to the surface, you can run rain on grid, and your boundary conditions will just be the connections to the surface. And so these are, curb inlets, these are graded inlets, access holes, that sort of thing. The boundary conditions for your pipe network can be just the surface connections. Also, you can have culvert openings, so these are kind of like the outfalls to your system, or maybe there's an inflow as well. So on the upstream end, a ditch that is flowing into a culvert into your system. And we can have connections to pumps within the conduit system. So if you have a wet well that you need to pump out of, I'll show you an example of that later, that is an appropriate boundary condition as well. But if you want to use external boundaries, you can. They are applied at nodes. And we have just the basic types. So you can get flow hydrographs, stage hydrographs, or normal depth. And what this allows you to do is bring in data from external sources. So if you wanted to model maybe your hydrology in HMS, and bring that data in and use that to drive your pipe network, this is where you would do that. So you'd add these boundary condition locations, and then you would point to your HMS results to drive your pipe network. Also, if you have an EPA SWM model and you wanted to use that to compare to your RAS model, you could bring in those results as well. We have a handy tool for that I'll show you. As we were in development and as we were doing validation, we did a lot of comparisons to EPA SWM models, because those are sort of the industry standard. And a tool we developed was to be able to import EPA SWM results. You have a SWM model and it has output, a .out file. You point to that, and what we'll do is we'll go in, we'll read all of the result out of there, and then we'll output it to DSS. And then if you already have a geometry in RAS, we'll automatically assign all of the observed boundary locations to the nodes in your model. And so this is really nice. You can very quickly get your SWM results into RAS, and you can compare them right in RAS in our hydrograph viewers. So it's a really handy tool for us as we were going through development, but we found that users really enjoy comparing those results as well. And so the message box on the bottom says, hey, we read the binary file from SWM, and it looks like you have 10 nodes in there, and 8 flows and 8 stages were matched in our system. And so we match those to our locations, and you get to see them right in RAS results. So speaking of results, access them mostly through RAS Mapper. And so like you have for 2D areas, water surface elevation, depth, velocity, that sort of thing, you get those for pipe networks as well. And you get a couple extras such as surcharge, percent full, that sort of thing. And so I'm just going to show you a little animation here. You can very quickly select conduits in RAS Mapper and then plot profiles from them. And you can see we're running this model with a rain on grid. and inlets are providing the boundary conditions into the pipe network. The profile on the right is showing you stages there, so the hydraulic grade line, but also along the conduit, we're showing you velocity and flow there, which is really handy as you're going through and debugging or even analyzing your system to determine where flow is going. Seeing that velocity and the flow right on the profile plot is very, very handy. Okay, so I don't want to ruin this for the next presentations, but this new coordinated plot, which we will talk about later in our webinar series, is super handy for plotting pipe networks. So you can very easily go in and select nodes spatially, and right away you'll get the hydrographs or profile plots for those nodes or conduits. And so once you select spatially, we will also show you which node you're selecting in the table on the left. And so you can either select from the table or you can select spatially. You can have multiple nodes or multiple conduits shown at once. And turns out this thing is very, very handy for pipe networks because you can get turned around a lot. There are a lot of nodes and conduits, and being able to select right from the map and from the table at the same time, very, very, very handy. So a big thing, particularly with urban modeling and analyzing pluvial risk, is that you need to be able to very easily visualize and communicate the outcomes of different study alternatives. And so with coordinated plot, with RAS Mapper, with our profile plots, you can very quickly and easily compare different study alternatives. And so I have an example here of rain on mesh model. This is our Davis example, and one is without a pipe network improvement. That is on the left. You can see depths are higher there. And then on the right, you can compare very quickly with this pipe network improvement. We've reduced flooding substantially, and anywhere spatially within the model, you can go and ask, hey, how well did we do here? How much did we reduce our flooding? And you can find that. It's very easy to compare alternatives. Now we are on to our example portion of the presentation. So really what I'm going to do is I'm going to walk through a couple examples and just show you different things you might come across while you're modeling pipe networks and how you might handle those. Our first and most favorite example model is Davis, California, for obvious reasons. And I'm going to look at just two places in this model. On the very downstream end first, I'll look there. That's the red arrow I'm showing you. That's the downstream end of the model. And then after that, we'll look at the circled area there to demonstrate the trunks and laterals. On the very downstream end here, our pipe network system is all converging on this storage node here. And so if you look at the mesh for the pipe network, you can see there's this black circle around that node there. And that's because we set a base area, a large base area for the node, and it is storing volume as the stormwater enters the pipe network and goes to the most downstream part. It's essentially a big wet well. So it's subsurface storage. The stormwater system drains to this large storage node, and then you'll notice that we have a pump connected to this node. And so we're pumping out of the node and into the channel to the north, and that's how this particular system works. And so the example here is you can very easily add a storage, we'll call it a storage node, so add a large base area to node, and then connect a pump to that storage and either pump it over a levee or pump it to an outfall channel close by. Another example here is sort of a detailed urban modeling situation with trunks and laterals. And so, yeah, this is Davis. This is just kind of a mixed urban area. So on the south side of the street, we have homes. You can see the cul-de-sacs there. And then on the north side, there's a school and a library. And you can see a trunk line running right down the center of the street. And then you'll see all these kind of nodes clustered in a few locations along the trunk. And those are laterals. Often, the crown of the road is pretty significant hydraulic control. So actually, in this case, it's nearly a foot higher than either side of the road, either gutter. The crown is nearly a foot higher. So when we're doing these urban models, particularly for like small cities or residential areas, you want to make sure if you have very large crowns or significant cross slopes, you want to make sure you align faces on top of those so that you're making sure to represent the hydraulic control there. In some cases, flow on either side goes different directions. And so it's important to keep that flow on the particular side of the street that it was designed for, and that the inlets on that side of the street were designed for as well. Back to trunks and laterals. So this is an example of our instantaneous conduits. So we zoomed in and we're looking at the conduits now, and you'll notice that, so for the little short laterals, they have these dashed lines on them. And that's because of our modeling approach. We've set those as instantaneous. And what that means is they are not a part of the hydraulic computations, but we're simply transferring flow from the inlet of the node to the receiving trunk node. And so you see each of these green start nodes, they have inlets on them. You know that because of the boxes around them. So as water exceeds the inlet elevations, either from the pipe network or from the surface, flow goes to or from that trunk node. But it's not a part of the mesh, or it's not a part of the hydraulic computations. So the reason we did that is so that you don't have to have these small, sometimes steep conduits inside of your mesh and make really small faces and drive runtime. So instead, you set them as instantaneous. And now you can still model these laterals without including them in your mesh. So I'm demonstrating that here. You can see the mesh for the trunk line, but the laterals are actually not included in the mesh. Something that's sort of fun that we're doing here is we actually are computing the property tables for these conduits. But what we do is we lump them into the receiving node. So that node that they're flowing into in the trunk line, those properties are lumped into that node. So it really is the best representation of the pipe network system still, but we reduce the complexity by pulling those out of the computational mesh so you don't drive runtime with small cells. And so on the upper right, you can see how to do that. It's right in our conduit attribute table. So the modeling approach, you get to choose between hydraulic or instantaneous. And for laterals, instantaneous is kind of the primary use case there. Moving on to a different example. So this is a very simple, small example we got from a user, and it's a detention pond. And so what we have is on the right, you have a pipe network that is flowing into this detention pond. So it's draining a larger stormwater network into the detention pond. And then on the left, you'll see that a little short conduit that is draining the detention pond into the channel. On the upstream end of that conduit is a riser structure. And so we've modeled the riser structure in RAS. I'm going to show you what that looks like. So what we did for this riser structure is on the node, we attached both a top inlet and a side inlet. So we're looking at the profile plot here. Top inlet is, you can see it's the triangle there. So I've kind of made them bigger so you can see them better. So the triangle is at the very top of that node. And then you can also see the side inlet. So that's the blue circle you have there. So that's our restrictor. It's a little orifice that is designed to very slowly bleed the detention pond into the receiving creek as to not have a very large hydrograph kind of flashing into the creek. So let's look at what the results look like from running this guy. So first, profile mode, downstream end, you can see that the tailwater from the 2D creek is just a little bit above our invert for our conduit. And on the upstream end, you'll watch as the very large flashy hydrograph comes into the pond, how the pond level rises and then falls as flow is going through the drop inlets and the side inlets. Okay, there it goes. It very rapidly rises, and then the top inlet is that overflow in it, and it's quite large. And so it can very quickly get water out of there. But then the side inlet is very slow draining. It's intended to drag out that hydrograph quite a bit. And you can see that there. And so if we looked at the flow hydrographs and compared the two, I wanted to show you kind of a side-by-side spatial and the flow hydrographs. The green hydrograph is the inflow, and you can see it's very, very, very substantial inflow, very peaky hydrograph. And the pink is the outflow. So that's actually what the creek is receiving. So we've done a really, really good job of chopping that peak off and dragging it out over a longer period of time. And I'll hit the animation there. So you can see the flow comes in very rapidly, stage rises in that pond. Then our riser structure is activated, and both the top inlet and the side inlet are flowing there and draws out that hydrograph for a long time. Okay, finally, I wanted to show you guys our junction loss calculations. Because we're geospatial, you can very easily look at your geometry of your pipe network and compute the losses due to angles at junctions automatically. So what we do is we're using the HEC-22 guidance. So this is the Federal Highways guidance for stormwater. In HEC-22, they look at angles from the outflow. So we look at the outflow conduit, that's the one on the bottom, and they compute angles from the outflow conduit. And based on those angles and the flow, a loss is attributed to the conduits that are flowing in. And so that's the diagram on the left. And then on the right, you can see I've got what on the top is just a straight run of pipe with a couple junctions in the middle. And then below that, I've got that same run of pipe, except I've made this really tight 45-degree angle between the first pipe, the inflow pipe, and then the second pipe. So very, very tight angle there. Automatically, what we'll do is we'll go and compute that angle. And based on the flow that's going through that conduit, we can compute a loss through there. And so what I'm showing you on the profile plot is the difference between the straight pipe, which is in the blue line, or the hydraulic grade for the blue line, and then the 45-degree angle in pink. So these losses can be pretty substantial. The modeling approach in other models is to try to look at what the junction looks like and then assign entrance and exit losses. And it's kind of squishy, not a defined science, but because we're geospatial, we can actually just look at the geometry, know the angles, and go to HEC 22 and say, all right, what is our loss that's happening at junctions? And it's really nice, and it'll have pretty substantial impacts if you have some tight bends in your system. Where do you find help? Well, we spent a lot of time working on the user's manual. We realized these are brand new features, and particularly for RAS modelers that are used to surface modeling, we wanted to provide you guys robust documentation to help you get started in pipes. And so the user's manual is really good to go through, and it's in the kind of a stepwise way that you would walk through building a model. So I recommend looking at that. The hydraulic reference manual is very detailed. It's going to tell you all about how we're calculating different boundary conditions at nodes, how we're calculating our hydraulic structures, that sort of thing. And so if you're into that you can find that in the hydraulic reference manual. But for example data sets and sample data sets, the guides and tutorials is really the place to go. And so I want to show you some examples of what we've got in there. So on the left, we're showing a user's manual and really giving you a great breakdown of all the nice features in order to help you build pipe networks quicker. And then on the right, I'm showing you the hydraulic reference manual and showing you the details of how we compute different boundary conditions at nodes. And then the guides and tutorials, we're actively adding more content to guides and tutorials, but we have complete tutorials from start to finish for importing a model from SWMM, attributing nodes and conduits, and then running simulations and looking at results. So that's a great place to start. If you've never done any pipe networks before, going to the guides and tutorials and walking through some of those will really get you started quick. We also have some sample data sets, and a couple of them we compare to SWMM data. So we have SWMM has some validation data sets that are extran validation sets, and we go through, we import those models into RAS, and then we compute them, and then we compare the results and kind of discuss why the results are different and where the models are good. I encourage you to look at that as well. So those are both in the guides and tutorials section.